At the beginning of this course, we discussed the Heisenberg uncertainty principle, and as you might remember, I showed you, or basically I told you, that the uncertainty of the position multiplied by the uncertainty of the momentum in the x direction, of course, this always has to be equal, greater or equal than h bar divided by 2. We talked a little bit about this and why this is so important in quantum mechanics, but I didn't really give you much of an explanation as to where this comes from, and that was because we didn't have the tools to do that back then. However, now we do. And for that reason, I now want to show you how to find the generalized uncertainty principle, because it is not only something that applies for position and momentum, but in fact, there exists this generalized uncertainty principle for any two operators. So we want to now see how this looks exactly and what this means. So in order to begin, let us just take any two operators. Let's call them A and B. And let's now create just some amount which we can call the uncertainty of A, which is going to be the amount that deviates from this operator, that this operator deviates from its expectation value, right? So we take the operator and we subtract the expectation value. And obviously if they are the same, there is not going to be any uncertainty. And for this to be, actually, we have to let it act on something. So let's let it act on some ket psi. So that's going to be our first uncertainty. We know that this principle is gotten, we can get it by multiplying these two uncertainties, because when we are doing a measurement, what we are interested in is to see what can we tell about different things simultaneously. So we don't only want one uncertainty, we want to have two that we can then multiply and see whether or not those observables are compatible. So let us then go for a second uncertainty, which will be sigma b, which will be defined in the same way. So just the operator minus its expectation value acting on psi. Okay, so now what can we do? Well, we know that we want to get to some expression that is of the form sigma a, sigma b. And well, there are several different ways to go forward. I think that one of the simplest ones is by using a trick, and is to think of the Schwartz inequality, which I discussed, I think, 1 or 2 videos ago. Now, if you don't know too much about it, I'm going to repeat it anyways, but that is what we're going to base this off. And the way to see it is that we have these two quantities here, and if we square them, then you can see that this is basically some, like, let's just call this f g g. So this would be sigma a squared, because it's squared, which means it's basically the inner product of something with itself, and sigma b squared is also the inner product of something with itself. And in fact, here we could see that g would just be this right here, ket of g, and the bra of g would be the bra of this right here. Okay, and similarly in this case, this ket of f, I said it backwards. The one with b would obviously be this one, and the one with a would be the one here. So what we did here is that we just wrote these square terms in terms of inner product. This is exactly the same. It's like saying the operator a squared is just a times a, right? But we used a different notation for the dot product or the inner product, which is this Dirac notation. But what does the Schwartz inequality tell us? The Schwartz inequality tells us that when we have these two different inner products, this will always be greater or equal than the modulus of the inner product between f and g squared. So that's what this the Schwartz inequality tells us. And this is what we now want to use. So let's see, I'm going to copy this, take it to the next page. And let's now work on it a little bit. So we now want to determine these quantities, and particularly what we are interested in because what we want to get to is basically sigma A, sigma B is going to be greater or equal than something, right? That's the point of the Schwartz inequality, because if we just get rid of this part right here, we are immediately left with, oh, I didn't erase the equal sign. We are immediately left with something that tells us sigma A, sigma B squared is greater or equal than something squared. So we can later just take the square root and we will find a relationship that is something like this. It's going to be greater or equal than something. So we need to determine what that something is. So we need to see this thing right here. Now, what is this? This is the modulus of some complex number. Remember, inner product is some complex number. So let's just call it, for example, z squared. Now, what is this? This is going to be the real part of z squared plus the imaginary part of z squared. And we know that this is always going to be greater or equal than just the imaginary part of z squared, right? This is obvious because here you take the imaginary part and you add something positive, so it is going to be greater than something that doesn't have this real part. So now we know that this part is going to be greater or equal than the imaginary part of what is inside there, which I'm just going to call z squared. Okay, and since this is greater than this right here, but this is greater than this, we can actually just go ahead and replace this. So we can just say sigma A squared, sigma B squared has to be greater or equal than the imaginary part of z, z being the inner product of fg squared. Okay, so we are slowly making progress because this is already looking simpler. Now, what is the imaginary part of some complex number? We can see it as the following part. So if we have some complex number z, this can be written as the real part plus I times the imaginary part. Right, that's nothing new. I hope you have seen this before. It's just, this is like 2 plus 3i, for example. And if we take its complex conjugate, we get the real part of z minus I times the imaginary part of z. So now, since what we want to do is to determine what this imaginary part is, then, well, all we have to do is we can subtract these two quantities right here. So when we do that, we get on the left-hand side z minus z conjugate. This will be equal to the real parts cancel out. So we get 2i imaginary of z. And we can actually eliminate this 1 over 2i. And this is our result. So let us now, instead of this imaginary part of z squared, write it as 1 over 2i z minus z conjugate, and all of this is going to be squared. Okay, so let us now take a look at what our current result is. Oh, I didn't erase this equal sign. Okay. So this is what we currently have. Let me now go to the next page. So what comes next? In order for us to actually find something here, we need to determine what z and z conjugate are. As we saw, z, we just defined it as the inner product between f and g. And z conjugate is going to be the conjugate of this. So that's going to be fg, right? Bra f ket g, and this conjugate, sorry. And what is this? As we saw in the previous video about Dirac notation, if we take the conjugate of this bras and kets, we actually can replace it by writing it as g f, right? The bra of g, the ket of f. Basically, we turned it around. And this is now something that we will have to calculate using the initial definitions that we used for f and g. Remember, f was this right here. This would be in the ket form, and this right here will be in the ket form of g. And you have to take into consideration, if we are going to use the bra version, we will have to transform it accordingly, remembering how to go from ket to bra. So let's go back here. These are our definitions. And well, what would be the bras? So for example, for f, the bra of f would be the bra of this psi. And then what do we have? We have the operator A, and you have to take its Hermitian adjoint. But now let's take into consideration that we are using this exclusively for what we call observable operators, right? These operators will give us observable quantities. And as we have seen before, these observables are come from Hermitian operators. Okay, so this right here means that the Hermitian adjoint of these operators for both A and B are just going to be the same vector because they are Hermitian, because they are observable. Okay, and this right here is just a positive number because the expectation value of a Hermitian adjoint, of a Hermitian operator, sorry, is a real number. We also showed that in a previous video. Okay, so we are going to get A minus this quantity. And similarly, in the case for G, we're going to get the bra of psi and then the same operator B because it is Hermitian minus the same real number. Okay, so now let us go ahead and let's find Z first. Okay, so let's go for Z, which we said is just bra of F, ket of G. So what is bra of F? It is bra of psi A minus the expectation value of A. And what do we have then? We have the ket of G, which is this right here. So this is going to be B minus expectation value of B, and all of this acting on the ket of psi. So now we have this product in the middle. Let's multiply through. So we got A B minus operator A expectation value of B minus expectation value of A operator B, and then we have plus expectation value of A expectation value of B, and all of this acting on psi. Okay, let me just make sure this times this minus AB minus AB plus plus. Okay, great. So now remember here the properties that we saw in Dirac notation. What we can do here is just separate each one of these quantities in their own, basically in this own little sandwich. So we get psi, and sandwiched in between we have AB of ket psi. Then we get minus, we can pull this constant minus 1 in front, psi, and what do we have here? Operator A, expectation value B, psi, minus, once again, psi, and what do we have here? We have expectation value of A, operator B, psi, and finally we have plus bra of psi, expectation value of A, expectation value of B, psi. So what can we do with this? Well, here, let's take a look at it. What we have here, A acting on B is basically another operator. So what we have here is just going to be the expectation value of this operator AB. So it's going to be the expectation value of AB. What do we have here? Take a look at this. What is the expectation value of B? The expectation value of B is just a real number. So it's a constant. We can just pull it outside of the expectation value. So we get minus expectation value of B. And then what are we left with? We are left with the expectation value of A. Similarly here, we can pull the expectation value of A outside of this, and we're going to get the expectation value of B. So we get minus expectation value of A, expectation value of B. But remember, these two are just numbers, so they commute. You can just flip them around as you please. So these two are actually the same. And finally here we have this is the expectation value of these numbers, right? But these numbers you can just pull outside, and then you just have this inner product between psi, and if the state is normalized, which is actually something that we are assuming here, because you can just go ahead and normalize wave functions. We have done it many times before, so let's not deal with the normalization constant. So in that case, we are going to be left with expectation value of A, expectation value of B. Okay, since they are just numbers. And from here we can see that these two cancel out. So this is what we are left with. This is our Z. Okay, so great. Now we could go ahead and apply the complex conjugate here, which is actually the fastest way to go about it. You could also use that this is going to be GF, but it isn't really necessary. It's much faster to just go ahead and apply the complex conjugate of what's going on over here. So when we do that, well, what is this going to be? Let's take a look at our result. So what we had over here, we have to apply the complex conjugate. So we have bra of psi, A, B, psi, right? I just wrote this once again as this, minus this quantity here. And we now want to apply the complex conjugate to it. So, well, I guess I should have started this in the next page right away. Well, whatever. Okay, so let us now conjugate all of this. In this first part, kets turn to bras, bras turn to kets. But since both are just states of psi, it looks the same. And now remember, what is A, B? If we apply this Hermitian adjoint, or we take this, we conjugate it, it's basically going to be B adjoint A adjoint, but they are both Hermitian. So it's just going to be B times A. Okay, so that's going to be what we get. And obviously the second part, this is a real number, so it stays the same. I'm going to write it as AB because, I don't know, I like it better that way, and since it commutes, it doesn't matter. And this right here is the expectation value of BA. Expectation value of BA. Well, these are operators, so I guess I shouldn't really drop the hats. So this is the conjugate. Now let us go back and see, where was it? Our formula, this right here. And let's begin plugging our results into it. Okay. So what is Z? Well, Z, as we saw, is this right here. AB, the expectation value of AB minus expectation value B, expectation value A. So expectation value of AB minus expectation value of A, expectation value of B. I flipped it here because, as I said, I like it better this way, but it doesn't matter. And then we have minus Z conjugate, which is going to be expectation value of BA. Do not flip it here, please. These do not commute, do not make that mistake. This does commute. And here we have minus minus, so we get plus expectation value of A, expectation value of B, and all of this is going to be squared. And here we can see that these two cancel out, and what we are left with is this right here. Okay, so we have that this uncertainty squared is going to be greater or equal to 1 over 2i times, and let's take a look at this. We have expectation value of AB minus BA, right? Expectation value of BA. We can rewrite this as 1 over 2i product of, this is just to make it very clear. Here we have AB minus BA acting on psi. All I did here is, remember, I just wrote each one of these in their explicit form, and then I applied the fact that of linearity of these Dirac notation. We already saw that property before, we know we can do that. And what is this in here? This is just a commutator between A and B, because that is just AB minus BA, right? So let us rewrite it. We get sigma A squared, sigma B squared is greater or equal than 1 over 2I. And all of this is then multiplied by, so here we have psi commutator of AB psi. So what do we have inside? We have the expectation value of the commutator of A and B. Let me see. Okay, there we go. And all of this is squared. And this is actually why I didn't apply the square before to eliminate this I, because now we can just apply the square root to all of this. And we will find that sigma A, sigma B is going to be greater or equal than 1 over 2I times the expectation value of the commutator between our operators A and B. I guess I didn't really need these parentheses. I'm going to get rid of them. Okay, so this is the generalized uncertainty principle. And this works for any two observables. And this is actually very, very, very interesting, because what this tells us is that if A and B commute, then sigma A, sigma B, right, this uncertainty will just be 0. Because the commutator would be 0, so all of this would be 0. So that actually tells us that if A and B commute, then they are compatible observables, which means that we can measure them at the same time. So that is something that is very, very important, and it will come into effect when we deal with angular momentum, because there we will have to find some compatible observables that we can actually work with. But that is for later. We could now go ahead and use this formula to show one example. I did a version of this in the previous video, so if you've already seen that, then, well, there's not much need to watch this once again. But in case you haven't watched it, I want to do it because it's kind of important. So let's consider that A is going to be the X operator. Remember, that's just X, basically, but that's what we did before. And some B operator, which is going to be minus I H bar nabla. Okay, so do these commute at all? Let's take a look at that. We did this part in the previous video, but let's do it again. So this is the momentum operator in the X, well, this is generalized, but obviously in the X direction, it's going to commute in the Y and Z direction. So we're actually only interested in that. So let me actually maybe rewrite this as just in the X direction. I guess it shouldn't be a partial derivative, but it's fine. So this is going to be minus I H bar derivative with respect to X. So we want to see what this commutator is. Now, as I mentioned in the previous video about commutators, if you want to find a commutator, you need to let it act on some test function. Otherwise, you might make a big mistake. So let's take a look at why that is important. So let's just use the definition of the commutator. So X times this minus this times X. So in the first case, we have minus I H bar. I put it in front because they are constants. They commute with basically anything, with any operator. And then we have X d by dx. Okay, that's the first part. Then we get minus this times this, but minus minus is plus. I can write the I H bar in front. And then here comes the important part. There's an F there, by the way. Do not forget the test function. Very important. Then we have the derivative with respect to X of X times the test function. Very, very, very important. You cannot forget the test function, because here it makes a difference, because otherwise this is just 1, right? And then you're going to get to the wrong conclusion. So the first part stays the same, minus I H bar X df dx. And the second part is going to be I H bar, the derivative of this. So we apply product rule. So the first part is just going to be F, and the second part is going to be plus X df dx. So here we can see that this right here will cancel out this, and our end result is just going to be I h bar f. And this, remember, is just going to be the commutator of the x and the momentum in x direction operators with some test function. So let us drop the test function, and we will see that this commutator is simply going to be I h bar. So let us now apply this to what we just saw. So when we do that, we see that the uncertainty between the position operator and the momentum operator is going to be greater or equal than 1 over 2i times the expectation value of the commutator. But this is just the expectation value of some constant, so it's just going to be this constant. So this is just I h bar. And this is just h bar divided by 2, since the i's cancel out. And this is actually what we saw previously. And we could now use this for any two operators that you are interested in. And I'm going to, in a video later, do this with the angular momentum when we are actually dealing with that. So now we are finally able to actually begin with angular momentum and then spin, which is going to be the final part of this first course in quantum mechanics. So I will see you in the next video.